In this video, what we'll do is take a look at process improvement data and test it for normality. If you've got business data, frequently it's going to be distributed like a normal curve, like a normal distribution. Um, but it'd be nice if there were some tests that you could perform to confirm whether or not it's normally distributed. If it is normally distributed, then we've got a wide array of powerful analysis tools that we can use. And if it's not normal, actually, that gives us a lot of great insight too in trying to determine what's not working in current state that we need to change in future state. So normality testing, important. The learning objectives will be to take a look at simple methods for testing for normality, including visual inspection. And then we'll compare that to statistical methods, including the Anderson-Darling test for normality and running a normal probability plot on our data set. All right, a couple quick thoughts about testing for normality using some simple methods first. One technique that we can do is take a look at the histogram and do what is called visual inspection. If the data set looks approximately like a bell-shaped curve, that is a test to determine if you've got normally distributed data. If it looks like a bell-shaped curve, it probably is a bell-shaped curve. You can also check for symmetry. Does the right-hand side look the same as the left-hand side? Um, Another simple test using descriptive statistics, mean, median, and mode is that all three should be approximately the same. Calculate mean, median, and mode for your data set if they're all the same. That's a strong indication that you've got normally distributed data. And in a separate video, we take a look at the empirical rule, the 68, 95, 99.7 rule. And we know that plus or minus one standard deviation, 68% of your data should fall within that range. 95% should fall within two standard deviations, and 99.7 should fall within three standard deviations. You look at your data and see if approximately that amount of your data falls within. Those are all great ways to determine if you've got normally distributed data. But there are statistical methods too. And so let's take a look at those as well. Two of the most popular statistical methods for testing data sets for normality include the normal probability plot and the Anderson-Darling test. Normal probability plots, the output is going to look something like this, and we'll describe how to read and interpret that in just a moment. And for the Anderson-Darling test, what we're going to do is a p-value method for interpretation. And I'll walk you through each of the approaches and describe to you what we're looking for and how you determine if the data is normal or not. Let's pull up some data right now. All right, I pulled up some of the course, one of the course data set files, the call center data. This is from the New Tech Wireless call center case that we explore in one of our programs. And what I want to do now is take a look at whether or not the data that has been recorded, whether or not it's normally distributed or not. So one of the first things that I can do is create a histogram, do visual inspection, do a mean, median, and mode test on it, take a look for symmetry. So I'll do that next. All right, so I've got a histogram up of that historical data, 700 plus data points, and I want to do some simple visual inspection and simple descriptive statistics to see if it's normally distributed. When you're running a normality test, there is no one way to run a normality test that is foolproof, that is always correct. It's the reason why we have so many different methods to test for normality. Let's take a look at visual inspection first. Does my histogram look like a bell-shaped curve? Well, I've got a perfect bell-shaped curve superimposed on top of the data, and it's pretty close. There are a few gaps here and a couple of overhangers over here, but it's definitely a mounted hump, so I'd say it passes visual inspection. Does it look symmetric? Does the right-hand side look like the left-hand side? And this blue line right here is the mean, and about the same amount as on the right-hand side as on the left-hand side. We can even do our mean, median, and mode test to get a better understanding of symmetry. We've got mean 99.66, median 99, and mode a little bit different at 105, but they're all pretty close to each other. So, I'm starting to feel good that this data is normally distributed, but again, there are some kind of gaps in the middle here, and there are a few times where the data is outside or more. We have occurrences that happen more frequently than what we expect with normally distributed data. So simple tools seem to show normal. Let's take a look at the Anderson-Darling test next to see if our data is normally distributed. Okay, so I've got all of my data, 700 plus data points highlighted. To run an Anderson-Darling test using QI macros, do the following. Go to QI macros, go to statistical tools, and then choose the descriptive statistics normality test. Now there's a whole bunch of information that is created when you do this descriptive statistics normality test. I'm going to zoom in so that we can see a little bit better what we've got here. A simple Excel histogram is created so that you can do some of your visual inspection approaches that we looked at earlier. You've got some of the descriptive statistics calculated as well. You've got your measures for central tendency, you've got a histogram, you've even got a box whisker diagram here. But to do an Anderson-Darling test, here's what we would take a look at. We'd be looking for a special statistic called the p-value right here. And we take a look at that p-value calculation. Now this is done by running a special Anderson-Darling formula on each of the 700 data points. We never do this manually. We always use software packages to help us out. The Anderson-Darling formula then calculates a p-value, and we're looking for p-values that are greater than 0.05. Now, the reason why we choose 0.05 is because we're typically running a test like this to be 95% confident that the data that we've got is normally distributed. And so we want a p-value that's 1 minus that confidence level of 0.95. So p-value of 0.05 or greater. P-values will always be between the range of 0 and 1. And what we want is a p-value that is greater than 0.05. And by taking a look at this at 0.26, that indeed is greater than 0.05. So our Anderson-Darling test shows that our data is normally distributed. If the p-value was less than 0.05, like 0.0001 or 0 altogether, or any value under 0.05, then we would say that the data is not normal. There are other ways, too, to test for normality using statistical methods. The Anderson-Darling test with the p-value is probably the most popular. There's also another test besides the Anderson-Darling test. It's called the normal probability plot. And if we zoom out here and scroll down, this is a normal probability plot. In a normal probability plot, we take each of the 700 data points, and you can see each of them here as little blue dots, and we take the actual value and we compare that actual value to what the hypothetical value would be if the occurrence was matched up against a perfect bell-shaped curve. The perfect bell-shaped curve is then transposed into this 45-degree line. I like to always think of it as take a bell-shaped curve and then snap it into a perfect 45-degree line. We'll call that a transformed bell-shaped curve. And we're going to compare where our actual data, the blue dots are, to the perfect bell-shaped curve, which would be the black line. Technically, it's called a residuals test. And what we're looking for is how many of these actual points that are in blue are pretty close to the line itself, and is there a randomness about the spread of those blue actual dots to the perfect bell-shaped curve. And what I see here is that this data is almost directly on top of the line. This is a really strong indication that we've got normally distributed data. If the points were falling outside of the line, way up here or down here, and there wasn't randomness to it, like we had a whole bunch that were up here to begin with, and then a whole bunch that were down here later on. No randomness to the data, then I would feel less confident that the data was normally distributed. And the final kicker for a normal probability plot analysis is to take a look at this R-squared value. This is a reflection of how many of the actual data points, when modeled up against the theoretical perfect bell-shaped curve, how many of those actual data points are reflected in the theoretical model. And what it's saying is that over 99% match up to the theoretical model. I use as a general process improvement rule of thumb, I feel pretty comfortable that I've got normally distributed data when the R-squared value is greater than 0.9. Other other process improvement experts will use 0.95. Others will use 0.85, but in my own practical experience, I find an R-squared value of 0.9 is pretty good indication that you've got normally distributed data. So normal probability plot, a little bit more visual, but using statistical techniques. Anderson-Darling test, more numeric, where we're just taking a look at the p-value calculation. All of them, though, Anderson-Darling, normal probability plot, mean, median, mode test, visual comparison, symmetry tests, they're all ways to help determine if you've got normally distributed data. And if a large majority of the tests show one way or the other, then that's the way that I'll go. If I've got one test that says maybe not normal, but then all of the other ones are saying it looks like it's normal, I'm going to go with the majority, because no one statistical or visual test technique is perfect. If it was, we would just use that one. It's good to have a suite of tools available when testing for normality, and now you've got a suite of tools available for you.